Welcome back to the fifth and final section of Chapter 2. In this section, we finally get to look at the derivatives of some trig functions. We're going to see sine and cosine coming at us by the definition, and then with those, we can actually find the other four using the quotient rule. So we're going to see why those work, because otherwise they're just kind of random. We did see the sine and cosine graphically how it makes sense, but graphically and actual derived using algebra are two different things. So let's take a look at some of what we're going to do. Now, a lot of what we're doing actually with these, like it's fairly basic finding the derivatives of these. In order to get much more in depth, we're going to need something that we're going to learn next chapter called the chain rule. So I say these are basic. It's still calculus, but the problems won't get very difficult here, relatively speaking. So learning targets. Find the derivatives of trigonometric functions. All right. Find velocity, speed, acceleration, and jerk related to simple harmonic motion. So that's the same stuff. It's just a derivative, the second derivative, and then we get to learn about a jerk. Some of you might be thinking, yeah, you are a jerk. Yeah, well, you might not be wrong. Find equations for lines that are tangent and normal to graphs of trigonometric functions. Same thing. To find an equation of a tangent line, we need a slope and the point. Once we find the derivative, we have the slope. We have the point. We've been doing this all chapter, even into last chapter. Nothing's changing except how we find the derivative. And then the normal, we just have to make the derivative perpendicular. Use linear equations to approximate values of trigonometric functions. And so the derivative of sine cosine, as we saw and as expected, the derivative of sine of x is cosine of x, and the derivative of cosine of x is negative sine of x. Now, why would these be? We're going to find the derivative of sine of x. So we're going to say f of x equals sine x. So the derivative will equal the limit as h goes to 0 of sine of x plus h minus sine x all over h. Now, we can't multiply this out because it's not a polynomial. So we have to find some other way of separating out that x plus h. If we remember back to our trig addition property that we learned about last year, we know that sine of something plus something is going to be sine of x cosine h plus sine of h cosine x. And then we have this minus sine x still in the equation over h. So that again is the sine addition property. I'm not doing the cosine one. You guys can do it. There's a cosine one that's basically the same. You can always look it up. It should be in your notes from last year. You should also have it as a lot of times these trig properties are actually in our textbooks. I didn't look. Not in the back, or it might not be in mine. Well, you can look up at the very least cosine addition, and in fact, the proof of cosine is not in the book. Okay. Anyway, you can look up the cosine addition ones. I don't want to give it to you because that's like giving away too much, and I want you to work for it because then you'll actually start remembering these properties a little bit. So we have f prime of x equals the limit as h goes to 0. Now what we're going to do is we're going to group some like terms, because we have a sine x here and a sine x here. So we're just going to move those over, and we're going to factor out that sine x, which will leave us with the cosine h minus 1. And then plus sine h cosine x all over h. We can split this up using limit properties. F prime of x equals, we're going to have the limit is h goes to 0 of sine x. We can pull that one out, times the limit as h goes to 0 of cosine h minus 1 over h, plus the limit as h goes to 0 of sine h over h, times the limit as h goes to 0 of cosine x. So we split these up. Notice each of the terms has a denominator of h. So once we split it with the addition, but then the multiplication, only one of those gets the denominator. So now if we take the limit is h goes to 0 of sine x. That doesn't have an h in it, so it's just sine x. Limit is h goes to 0 of cosine h minus 1 over h. This one we don't know right off the top of our head, but if you explore it graphically, if you graph it and you look at it, you will see that that is getting closer and closer to 0. Plus, limit as h goes to 0 of sine h over h. We have actually seen this one, but again, looking at it graphically shows that that'll get you to 1 times cosine x doesn't have an h in it, so it's just cosine x. Well, sine x times 0 is 0. 1 times cosine x is cosine x, so f prime of x equals cosine x. So that shows that. What are some types of derivatives you'll have to find? Things like f prime of x equals 3 cosine x. Well, a number in front's just going to stay in front. Oh, no, that's f of x, not f prime. That's just f. Because now f prime of x is going to be 3, and then what's the derivative of cosine x is negative sine x. So we'd have negative 3 sine x. That would be the velocity. If this was a simple harmonic motion problem, where f of x is the distance, that's the velocity. The acceleration, we would take the derivative of that. What's the derivative of sine? Just cosine. We have this negative 3 in front, so it's negative 3 cosine x. If we want to take the derivative of that, derivative of cosine is negative sine, so that just makes it positive 3 sine x again. And it'll just keep repeating like that when it's just a sine or a cosine. Other thing we could do, we could say f of x equals x squared sine x. Now all of a sudden we need to use product rule. Let's have u equal x squared, v equals sine x, means du will be 2x, dv is cosine x. So we can multiply and multiply. Again, I usually do that like positive, like I usually do this one first, because with a quotient rule, the order is important. So we get f prime of x equals 2x sine x plus x squared cosine x. There we go. It's product rule. So those are the types of derivatives you'll be taking. You won't have to worry about anything inside of the sine or cosine yet. That'll be next chapter. We will be using these quite a bit, so getting familiar with them is going to be beneficial to you. So the derivatives of the other trig functions. First, we have a vocab word, that jerk. So a jerk is not just a math teacher. No, it has other definitions. It is the change of acceleration. A jerk is a small change of acceleration. So it's a derivative of the acceleration, which is the third derivative of the position function, which could also be written as this, d3s over dt cubed. And so that's what a jerk is. You may remember I have a t-shirt that says, "Don't call me a," and then it has that equation on it. So it's "Don't call me a jerk," but you know, sometimes. So what are the derivatives of these other trig functions? I'm gonna prove a couple of them on the next page, but right now we're just gonna look at them. So the derivative of tangent is secant squared x. The derivative of cotangent is negative cosecant squared x. So if you think sine gives you cosine gives you negative sine, it kind of switches. Well, tangent gives you secant squared, cotangent gives you cosecant squared, but it's negative. Cosecant, or secant x gives you secant x tangent x. If you had to take a guess as to what cosecant x is, what the derivative is, can you guess based off of the patterns we've seen? Cosecant will be negative cosecant cotangent. So again, like if you know secant is secant tangent, that means cosecant gives you the co to both of those, and also all the cos are negative. The derivatives of all the co-functions are negative, whereas the derivatives of all the non-co-functions, the sine, tangent, secant, are positive. It's almost like they were actually named with some thought put into them. I know in trig it doesn't necessarily seem that way. They seem really random, but they aren't actually random. They do have all sorts of reasons for why they're named that way. So let's take a look at a couple of these. We're going to look at tangent, and then we'll look at cosecant. So tangent, we can rewrite as sine of x over cosine x, which means we have quotient rule. So u will equal sine x, v will equal cosine x, du, it's a derivative of sine's cosine, dv, derivative of cosine's negative sine. And so now we're going to do this one minus that one. So f prime of x is going to be cosine times cosine. That's cosine squared x minus sine x times negative sine x will be plus sine squared x all over. We have to square the bottom, cosine squared x. And you might think like, wait a second, in my notes, which I'm sure I'm writing down correctly and at all, my notes say that the derivative of tangent isn't this, it's secant squared. Well, we have some simplifying we can do. The first thing we're going to look at is this numerator here. Because what is sine squared plus cosine squared? Oh, that's one of those identities, one of those ones that were super important, like the couple I told you we needed to know all the time. Oh, that's the Pythagorean identity. Sine squared plus cosine squared equals 1. So this is 1 over cosine squared x. Well, 1 over cosine is secant, so 1 over cosine squared is secant squared x. And there we go. That's the derivative of the secant, or of the tangent. And that's why it's secant squared. It's because of that square in the denominator, then the numerator actually simplifies to 1. How about the derivative of cosecant? So cosecant is 1 over sine of x, which means that in our quotient rule, u will be 1 and v will be sine of x. Means du, the derivative of 1 is just 0. dv will be cosine x. So our derivative, we're going to have these two. So 0 times sine of x is just 0, minus cosine times 1 is cosine x, over square the bottom, sine squared x. So the 0 is just 0, so that's 0 minus cosine. So we can simplify this a little bit to be negative cosine x, and that's where that negative comes from, by the way. It's that minus in the quotient rule. So negative cosine x over, instead of writing sine squared, I'm going to split that up. We're going to write it sine x, because we could have that as cosine x times 1, and now all of a sudden negative cosine x over sine x is negative cotangent x, and 1 over sine x is cosecant x, which is just the flipped order as we had on the other page. I usually put the cosecant first. There's no reason for it other than that's how I remember it, because multiplication is commutative. But that's how we can get the derivative of a cosecant as well. The cotangent and secant functions can be derived the exact same way. I would recommend doing it just as practice. See if you can get to the actual values. It will be good for you to do it, and I strongly recommend it. Now, second derivative. So finding the second derivative, which we can do that. So to find the second derivative, we're first going to find the first derivative. So I'm going to take it over here. We're going to go f prime of x equals the derivative of secant x is going to be secant x tangent x. Easy enough. Now for the second derivative, now we have a product rule that we have to deal with. See how these come up all the time, just randomly? What's fun is when we get product rules inside product rules inside product rules. That gets a little bit complicated, but fun nonetheless. So now we have a product rule for the second derivative. So let's have u equal secant x, v equal tangent x. So du, the derivative of secant, is secant x tangent x. The derivative of v is secant squared x. So our second derivative now, we're going to have this times this. That's going to be secant x times tangent squared plus that times that, secant cubed x. And there we go. Yes, we could factor out a secant if we really wanted to. It's possible that maybe it would simplify, but this one does not. Now, if you are finding the tangent line at a point, you would just plug in your point to this and get your slope of a tangent line. If you're estimating what a value would be, you would find a line, and then at a certain point, then you'd plug in something just a little bit more than that. So if we wanted to estimate, let's go cosine of 0.1, we would first find the derivative at a point near 0.1 that we can do something with. Something near 0.1 is going to be 0. So we would say, let's see, f of x equals cosine x, so f prime of x is negative sine of x. F of 0, cosine of 0 equals 1. F prime of 0, sine of 0 equals 0, so that's just 0. This is not the greatest example because we just have a horizontal line here, but whatever, it will work. So what we would do here is we would make our equation. We have our slope and we have our point. So we're going to go y minus 0 equals 0 times x minus, no, x minus 0, y minus 1. I'm fired. So we would plug in our points. I would leave this in point slope form. Now, right now, being that the example I chose, we have a horizontal line, there's a lot of zeros in here, and so I'm not going to simplify this because we're going to follow through with what we would do so you can see what it is that we would do. So we'd get our equation right like that. Now we would plug in the value that we're looking for. This is 0.1. And what's going to happen when we do that is this part of it, this 0.1 minus 0 in our case, but whatever's inside these parentheses, that'll give us the difference between the point that we found and the point that we're looking for. So it's going to hopefully be a fairly small distance. And then we'd multiply by the slope and add whatever this number is to the other side to get our estimate for y. This is what's called linear approximation. It can be useful. It was way more useful before we had technology that would find us stuff, but it is still useful at times, and there's generally a problem or so on it, like a multiple choice problem on the AP test, and like part of another problem. So like 2 points or 1 point in the free response section. So this would be section 5. This would be looking at all sorts of derivatives of trig functions along with a couple other ideas. I will catch you in class, but until then, keep working problems, keep asking questions, and as always, happy mathing.